Good morning, everybody. I would like to present you today the results of my current research project, which is running since 2.5 years. So it's still, we are gaining still results. So, but I want to present you today some of our current results. This research project copes with the impact of processing on the content of essential and toxic elements in fruits and fruit juices, nectars and smoothies. So why do we have this research project? What is the background of it? At the moment there's a worldwide trend to decrease the natural limits of heavy metals in foodstuff, especially in fruits, also of arsenic. This is not a heavy metal, but the natural limits for arsenic should be limited as well. And there have to be solid data to provide the industry which reduction are achievable and which not, and how the processing, for example, affects the later concentrations in the product. And there's also only scarce information on the element concentration of purees and smoothies. And there are also some new processing procedures, processing techniques and processing aids which have to be characterized. And this is something we deal with in our research project. First of all, of course, before we have a closer look at the juices, we have to know what elements occur normally in fruits. So that's why we have to gain a solid database for common ranges of various elements in certain fruits. And there we focus on apples, on berries, grapes, but also on pineapples and sour cherries and pears. And then a further aspect of our research project is the influence of dejuicing. So what happens if you press a fruit, which elements go really into the fruit juice and which elements stick to the pomace. And we have also a closer look at different processing techniques which are common in fruit juice production and also on the processing aids. If you have a look at the elemental composition of juices or of fruits, you could almost find half of the periodic system within these products, if your method is sensitive enough. Nevertheless, most of the data which are at the moment available focus on those metals which are obviously toxic, for example, arsenic, lead, mercury, cadmium, and aluminum, or those metals which have a nutritional value, for example, magnesium, potassium, calcium, iron, copper, and zinc. But there are also several other elements present in the foodstuff where only scarce information is available. And so we developed a method which focuses also on various other elements which are the most abundant ones in our products. These are at least 26 different elements, and to analyze them we have to develop a method which covers a very wide range of different concentrations in an order of over 6 orders of magnitude, sorry. Because we want to analyze on one hand contaminants, where we have to be very sensitive with concentrations of 2 microgram per kilogram, but on the other hand, within the same method, we would like to analyze minerals, which could be quite abundant in those products. For example, in case of potassium, we have concentrations of up to 2 grams per kilogram. And the products we cope with are juices, of course. This is a very simple matrix because it is quite homogeneous, it's already liquid. But fruits and mash or purees have to be there have to be a special sample preparation for the analysis, of course. So that's why I want to show you some details concerning our method. For the elemental analysis, we do a microwave digestion, And such a microwave digestion is to dissolve metals in the presence of organic molecules by thermal decomposition. This means that all organic stuff within the sample, for example, fibers, endocyans, sugars, organic acids, are destroyed by the use of an organic acid. Therefore, we have to put all these compounds, our sample, the organic, the nitric acid, and water into such PTFE vessels. You can see them here. And these PTFE vessels can be hermetically closed, and they are later on or subsequently put into a microwave. And the microwave irradiation raises the temperature within these closed vessels, and also the pressure, so that we can reach temperatures up to 180 degrees, and this destroys all the organic compounds, so that we have in the end only dissolved metal solution. So for example, here you can see this very clear solution. This I can't remember yet, but it could be also blackcurrant mesh, for example, because all of the organic compounds are destroyed and we have only dissolved metals. The subsequent measurement is with ICP-MS, so I prepared also a few slides concerning this. What means ICP? ICP is an inductively coupled plasma. We produce our plasma with an argon gas. In this case, we have to use very high amounts of argon, of 15 liters per minute. And this argon gas is ionized by a spark. And the produced argon ions and electrons accelerate in a highly changing radio frequency magnetic field, which is induced by such a coil. And this fast acceleration and collision of the argon ions and electrons produces very high temperatures of up to 6,000 Kelvin, which is comparable with the temperature on the surface of the sun, so quite hot. And our dissolved metal solution, you can see here this schematic illustration of such a plasma. This solution is pumped into a spray chamber, nebulized, and some little drops of the aerosol enters the ICP. There it produces single charged ions, and these single charged ions are later on or subsequently measured by mass spectrometry. We have here the possibility to deflect the charged ions, to separate the charged ions from non-charged particles, for example photons, and subsequently in our system works with a quadrupole. Subsequently the metals are analyzed to do their mass to charge ratio. Now I would like to show you some results concerning the analysis of different kinds of fruits, because like I already told you, it is important if you would like to evaluate concentrations of elements you find in fruit juices, for example, or other products made out of fruit. You have to know also the original concentration which normally occurs in fruits, so you will see later on what I mean with that. In our research project, we mainly focus on European fruits, so for example apples, pears and berries, but we included also pineapples, which might be also of interest for you, so that's why I prepared these data for you. But why have we focused on pineapple? It is known that pineapples accumulate manganese in a higher extent than other fruits. And so pineapples in an immature stage, for example, can accumulate, for example, up to, the literature says, 40 milligram per kilogram. This is one effect is because of acidic soil conditions, which influence the uptake of elements from the soil, and yes, which might take place also in case of pineapple. In the following slide, I prepared a principal component analysis of course, pineapples, but pineapples mainly from Thailand, but I had also 6 samples from Costa Rica compared to the elemental composition of apples and berries. The berries we analyzed here were, we included different kinds of berries, so strawberries, raspberries, blackberries, blueberries, and black currant, for example, and were from different areas from all over Europe. So it was not a very focused data set. And we mainly focused on these elements. And here you can see the separation. You can see that apples can clearly be separated from all the other groups. So they differ very clearly in their elemental profile. But also the pineapples from Thailand and those from Costa Rica can be separated. Of course, we only analyzed only 6 samples from Costa Rica, so it would be good to have a bigger data set to make this comparison, but this was not the main focus of our current research project. This was just something I thought might be interesting for you here. And like I said, the berries were quite inhomogeneous in the data set, and this is also something what you can see here. So let's have a look which elements make the separation. And there is the loaded. Here you can see the loading plot, which elements describe mainly the different separations. And you can see here that most of the elements, or all elements, are on the right side. This is because apples had only very low amounts of all these elements. These elements were mainly abundant in the berries and in the pineapple samples, and that's why these elements described the pineapples and berries, but not the apples which were here in this area. And you can see the pineapples from Thailand, they were here in this area, so they are mainly described by rubidium, manganese, potassium, and magnesium, for example. And those pineapples from Costa Rica were mainly separated because of their iron content, copper, and, for example, barium. I prepared also a few slides to have a closer look at the data, because sometimes in these other diagrams it is difficult it is just good to have an overview, but if you want to know more about the results, you have to have a closer look at the data. And here, for example, you can see so-called box whisker plots for the manganese concentrations found in apples, berries, and the pineapples from Thailand, and those from Costa Rica. And like you can see here, the pineapples from Thailand had a higher manganese content than those from Costa Rica, but also berries, for example, have high amounts of manganese, whereas apples have very low concentrations. Manganese itself is an essential element. It is important for many enzymes in the body, but it has also some toxic effects at high concentration and at a long-term exposure. But mainly if you inhale, for example, manganese, then it can cause, for example, Parkinson's disease. Nevertheless, there are so-called estimated safe and adequate daily dietary intake levels, which are set for adults at concentrations of 2 to 5 milligram manganese per day. And also the WHO recommended for the tolerable daily intake of manganese of 3.6 milligram for adults. So the manganese content, which is already present in some foods is comparably high to those concentrations which are recommended as an upper daily intake. In case of rubidium, you can see as well that this element is very present in those pineapples from Thailand, less present in pineapples from Costa Rica, but still very abundant compared to the rubidium concentrations, for example, found in apples and berries. Rubidium is supposed to be possibly essential. It is not known yet, but it is very similar to potassium, for example, and so it has the interchangeability with potassium and interacts in different biological systems like potassium, but there's little evidence for any toxicity. So quite an interesting element. And in case, for example, for iron, we can see here, for example, that the iron concentrations in pineapples from Costa Rica are higher than those from Thailand. Berries had the highest concentration of iron, and less was found in apples. And like everybody knows, iron is very essential. It's involved in the DNA and enzyme synthesis, in the oxygen transportation, and so on. So a quite high nutritional value. But what happens if you dejuice, for example, a fruit? So if you produce a fruit juice out of a fruit, which elements really go into the liquid phase, and which elements maybe get bind to the pomace because of all the fibers and so on? This is something we wanted to have a closer look at. It is, and therefore we have in our institute a pilot plant to produce fruit juices with different processing lines. And the systems we are using are very similar to those systems which are used, or they are equal to those systems which are used in the fruit juice industry. So we can produce really in a small scale those juices. Here, for example, you can see such a Bucher press, which produces the directly pressed juice. And this system works in a scale of 250 kilograms, so already in a very high juice producing scale. If we want to see what elements are transferred into the juice, of course we have to analyze the mash on the one hand and also the juice on the other hand. And of course it is also good to have a look at the pomace. So in the end, the summary to the sum of the amount which is found in the juice and the pomace should be, of course, this what was originally found in the mash. And this is, of course, quite challenging if you think of the scale we are working in, because we are working in a 250 kilogram scale, and we only need very small amounts for our analysis. And so it is quite a challenge to have a good recovery. But now I would like to show you how the concentrations changes. So here you can see, for example, the concentration of a typical apple mash. So this is also equal to those elements which are found also in apples. For potassium and calcium, which are the most abundant elements shown here, and the other ones which I wanted to show you are iron, rubidium, manganese, and barium. If we do now this dejuicing step, you find a reduction of the elements into the juice phase. So the concentrations here, you can see the concentration which is originally found in the fruit, and this is the concentration which is later on found in the fruit juice. So you can see, for example, in case of potassium, that we have a reduction to 87%, which is later on found. Also in the case of rubidium, we have still a very high transfer, so there's still a lot of rubidium which goes into the liquid phase, or into the juice. But some elements are really clearly reduced. For example, in case of calcium, you find only 50% of the concentration which is originally in the fruit. You find only 50% later on in the juice. And this is more, this effect is more clearly also for iron and barium. Here you find only 30% of the concentration which is originally found in fruits later on in the juice. So there is a high reduction of the iron concentration, and especially in case of barium, it is clearly reduced. So, and of course, if it is decreased in the fruit juice, it increases in the pomace, of course. And so the pomace, for example, in case of barium, is quite rich of this element. Barium, for example, is there is not any biological role at the moment known. So it's supposed to be toxic, but it has no nutritional value. Barium, for example, interacts with the ion channels normally for potassium and block them, and has a high activity because of this on the nervous system, for example. So it's a quite toxic element, and that's why it is good to reduce it by this reducing step. But something what you have to keep in mind is, if you concentrate some elements, for example, later on in a pomace, this pomace is sometimes used for other reasons, for example, for animal feeding and so on. And these pomace, of course, is maybe rich of some also toxic elements, and this effect also occurs in the case of mycotoxins, for example, that they are concentrated in the pomace, and also in the case of pesticides. It's just something to keep in mind. What happens, for example, if you produce not a juice but a puree? A puree is normally a fiber-rich product. The industrial production of a puree is done with a finisher where the fruit pulp is forced through a sieve. And so we have here a higher content, of course, of fibers and a very low amount of press residue. And in this case, of course, which should be also quite obviously, the amount of elements which are transferred into the puree is much higher than those elements which are found, for example, in fruit juice. So we find here 80% of the 80% of the original concentration in average, which is normally abundant in fruit, later on also in the puree. So, for example, in case of iron, we can see that fruits itself has the highest content, for example, in iron. The puree is a little bit less, and the lowest iron concentration is found, for example, in fruit juice. But something we don't know at the moment is, for example, the bioaccessibility, because even though the concentration of iron is lower in the fruit juice, also the metrics changed. So you have also less fibers, and maybe the iron from a juice is better bioaccessible or bioavailable than the iron from the fruit, for example. And this also could be not only for iron, but also for the other elements. In the next slides, I would like to show you the effect of the processing. For example, in Europe, but also in North America, it is common to drink also clarified juices. I think, for example, clear apple juices are also common here in the supermarkets. And to produce such a clarified product, it is important to do furthermore processing steps to have a real stable and clear product. I just want to explain a little bit concerning this processing. To produce a clear juice, you have, of course, the juicing step. In this case, you have at first a cloudy juice. This cloudy juice has to be enzymatically treated with the pectinase and later on fined. This fining is to reduce phenols and proteins which could lead to a turbidity. And in this case, to find the product, fining products are used, for example, gelatine, silicazole, and bentonite, which reacts with these phenols and proteins and build little particles. These particles are later on separated by centrifugation, and then there's a further filtration step. And there's different kinds of filtrations, and some filtrations need so-called filter aids. Filter aids are also processing aids, particles which are used for the process but shouldn't stay in the product. These filter aids are, for example, diatomite and perlite, and the product after filtration is of course pasteurized, and you have your clear juice. The most critical steps within these processing are the use of bentonite, diatomite, and perlite, because these products are from geologic origin. This means, for example, bentonite is a clay mineral, and if they are not really pure, so if the quality is not good, they can release some elements which are normally common in the soil, and also in this case in bentonite, diatomite, or perlite. And it is known, for example, in case of these processing aids, that they can release elements like lead, arsenic, and aluminum. And that's why there are some purity requirements to control the food safety. So the supplier of these products have to control their own products, whether they fit these purity specifications. But these analyzers, of course, they are very targeted, because everybody knows, okay, diatomite, for example, can release arsenic, and bentonite can release lead. But of course, like I already said, there are so many other elements where we have to have a look at, and that's why we did a non-target analysis. But we did this analysis with another technique. This is called TRXF. That's why I want to say something about this technique as well. This measurement technique is a total reflection X-ray fluorescence analysis, and it is completely different to the ICP analysis, and it is sometimes good to have two independent methods available to make a double check for your results. So that's why we have different possibilities to make elemental analysis. This method copes with a spectrometric method. It is a spectroscopic method, sorry. And what does it mean? We work here, like the name already says, with X-ray radiation, and you can see here the model of an atom, the Bohr model, and the X-ray radiation is of course high in energy, and that's why it is possible to make an ionization of atoms by removing electrons from the inner orbitals of the atom. But this is of course a quite high impact on this atom, and the atom gets unstable and tries to restabilize. And this restabilization is done as follows. An electron from a higher orbital jumps into this lower orbital, and because these higher orbitals have higher energy and these these orbitals have a lower energy, the energy different is released, and the energy different is specific of the kind of element. So that's why we can differentiate, so we can measure all different elements parallel and differentiate them because of the different energy release, and the amount, of course, correlates with the concentration. How does this measurement work? The sample preparation itself is very simple. For example, if you have a liquid product, maybe you have to dilute it. If you have, for example, solids, like in our case the filter aids or the bentonite, it has to be suspended in a solution. Later on you can add an internal standard. We, for example, we use selenium in our case. It is afterwards homogenized, and then only a few microliters of the sample, so 5 to 10 microliters, are piped on such a sample carrier and tried. You can see here, for example, the illustration of such tried droplets. And these little sample carriers are later on transferred just in the spectrometer and measured as follows. You can see here the sample carrier. You need an X-ray tube to produce the X-ray radiation, which is selected by a monochromator. That other radiation is removed, and we measure with a total reflection technique. This means we have to have a very low angle of incidence, that the total reflection occurs. This means that the X-ray beam just goes over the surface and not too deep into the sample, because by doing this you have no effects of the matrix in this case. And of course we are measuring the fluorescence later on, so that's why we measure it in a 90 degree angle with the detector. The pros and cons of this method is that we need only very small amounts of sample, and we can measure also solid material without microwave digestion. In case of ICP-MS, we always need this dissolved methods, which have to be pumped and nebulized and so on. And here we can measure also non-digested solid particles, for example. But the cons of this method, so which is not so good, is that we can only measure or we have good results for all atoms with atomic numbers higher than potassium. So for example, for aluminum or sodium, lithium, we get only we get not so good results in our quantification. Now I would like to show you the results of the non-target analysis of the different filter aids by this technique. Here you can see diatomite, and here you can see perlite. And if you have a look at the median, you see that diatomite has the average amount of the different elements which are shown here. It has, in most cases, higher average amounts than perlite, except of rubidium, for example, and what was the other one? Lead. But what was quite interesting is that vanadium, for example, is much more abundant in diatomite than in perlite. But nevertheless, these are just the filter aids, and we can see, okay, this filter aid has a lot of vanadium, but this doesn't mean that this metal really goes into a product. It is just rich of this element, but it's not really, it is not known whether it is released. So that's why we did filtration experiment, I will say something to this later on. Just I prepared something to show you first what the difference is between diatomite and perlite. Diatomite are fossilized remains of diatoms. So these are microalgae which are fossilized. You can see here such a picture. They have quite nice structures and they very different particle sizes, which is very important for the filtration to have a good filter cake. And perlite, for example, has a completely different origin. Perlite is a kind of volcanic class in this case. You can see here also the main compositions of these different filter aids. For example, we have higher concentrations of these aluminum oxides in the perlite samples than in diatomite. Like I said, we did some trials with filtration trials with our pilot plant, and here we have done so-called pre-coat filtrations, which is also very common in the industry. And by using this filtration technique, we have to use the filter aid as a pre-coat layer, and the juice is filtered through this filter aid layer. We use this, we have done these trials in a scale of 200 liter of apple juice and in a 3-fold repetition. And here I just wanted to explain the technique, how it works. We have a so-called candle filter, which is like a steel tube with many pores, so like a sieve, which is here, this. And the filter aid layer is adjusted on the outer side of the candle filter steel, and the juice, which has to be filtered, comes out also from the outer side with all the cloud particles. And of course, there is a deposition of these cloud particles on the filter aid layer, and we have to, in case of this filtration technique, we have to add some filter aid also to the juice to have a good filter cake with still some pores inside, that the filter cake doesn't get too fast too clogged. And afterwards, the filter juice rinse through the inner side of the tube, and we get our clear juice. For our analysis, we analyzed, of course, the cloudy juice and the clear juice after filtration, and this is what I want to show you here. Here you can see, you already see that the scale of the diagram is a little bit weird at the moment. You can see the concentrations of the elements in the juice before filtration. I focused here on arsenic, molybdenum, lead, titanium, and vanadium. And after filtration, you can see that several elements clearly increase. Of course, we can see an increase of arsenic. This is already known. Nevertheless, the maximum limit for arsenic, for example, in juices is 50 microgram per kilogram, so it's still not really relevant. We can see also an increase of molybdenum. There's no effect on lead, for example, an effect on titanium, but we can see also very high impact on the vanadium concentration. Vanadium in an unfiltered juice, but also in fruits itself, occur in very low concentrations of less than 5 microgram per kilogram. And you can see here in this case, of course, we used the diatomite with the highest vanadium concentration in the TRXF analysis, but you can see a very high impact on the vanadium concentration after filtration. This concentration can be, of course, it is affected depending on the kind of filtration. So we did also different kind of filtration techniques in our pilot plant. We tested also different kind of diatomite products, so those which had lower amounts in the TRFR measurement, showed also a lower amount of vanadium in the later juice. And it also depends on the dosage of diatomite which is used for the filtration. Sometimes you can use also a little bit less of the filter aid, so this has also an impact, of course. But you can, if you use, for example, another filter aid, we tested, of course, also perlite, you see that the elemental concentration nearly doesn't change. So there are some elements which are also reduced by the filtration, because the filtration is also a removement of some cloud particles, so also some further elements might be reduced. But you can see also that other filter aids, for example, don't lead to this high vanadium concentrations in the final product. We checked also some commercial products. You can see here, for example, the average vanadium concentration found in cloudy apple juices. So these juices, of course, are not filtered. That's why we find normally very low concentrations. This sample might be a blend of a cloudy juice and a clear juice. It was a commercial product, so we don't know it, but maybe the company who sold this product wanted to have a special amount of cloudiness in their product, so maybe they did this type of blending, we don't know. But you can see that clear apple juice products really have, in average, much higher concentrations of vanadium than cloudy ones. But this technique is also used for wine production. It is also common to filter wine, but also to filter beer. And in all these products we find vanadium over, of course, a broad concentration range, because the filtration with diatomite is, of course, only one kind of filtration technique. Some companies maybe filter with perlite, or some companies also do membrane filtration. Membrane filtration is another filtration type where you don't need any kind of filtration aid. So you don't have this effect that maybe some elements are released into the product. But I wanted to show you a few facts about this element, because you see that we have, just by using this one processing step, we have a high impact on the concentration which is later on found in the product, which is naturally not occurring in foodstuff. Normally the literature says that the common Western diets lack of vanadium, because a lot of products have very low concentrations of this element, especially vegetables, fruits, and meat. But also, for example, water, they have in average less than 5 microgram per kilogram. There is some literature which is already more than 40 years old, which says, okay, there are some beverages which contribute to a considerable proportion of vanadium, of the vanadium intake. So they already said, okay, there are some beverages which have high amounts of vanadium, but nobody has known up till now where it came from. There's an average daily intake of approximately 10 to 100 microgram vanadium per day. And it is known that it is a trace element, the daily intake for its essential to be essential should be at 10 microgram per day. Vanadium itself has a very high so vanadium, of course, if you to have the concentration of an element is one fact, but you have also to have you should have a look at the kind of element, how it occurs, so the oxidation stage, the binding form, and so on. And in case of vanadium, there are different oxidation stages present. It has a very high redox activity, and because of that, it has a high pharmacological activity. For example, vanadium tends to be oxidized to vanadate, and as vanadate, it is very similar to phosphate, and so it binds to all the phosphate binding enzymes, and it has a stronger binding than phosphate, and it can block these enzymes because of that. Furthermore, for example, it also binds at the insulin receptors and works like insulin in this case. So it has very high biological activity, but nevertheless there is a so-called upper daily intake level, which is set to 1.8 milligram vanadium per day by the Institute of Medicine. So this is still quite high to those amounts which we find in fruit juices in the case of the filtration of a high contaminated diatomite. For example, the filtration trials we have done before with concentrations of up to 200 micrograms per liter later on, you have to drink, you have to drink 9 liters of this apple juice to reach this upper daily intake level. But nevertheless, for example, in Germany, there's at the moment a so-called action level for vanadium in drinking water by the Federal Environmental Agency, and they said that drinking water, for example, is not allowed to or shouldn't contain more than 4 micrograms per liter, because there's at the moment the discussion that it might be toxic. It is not really known what the effect is. So there are some literatures which say it's essential, some literatures which say there is some high biological activity, but it is not really known yet. And so, for example, this action level for drinking water is 4 micrograms per liter. And if we compare it with our beverages, with juices, with beers or wine, the really occurring vanadium concentration can be much higher if such a filtration step is used. But where does it come from? Why is vanadium in this diatomite? It is known that vanadium itself, it is quite common in the soils. There it is as abundant as zinc, for example, but it has a poor mobility. But it is also very abundant in the sea. There it is the second abundant trace element. And some algae accumulate specifically vanadium because of its high redox activity. It is important for some enzymes within these algae. And if you remember, diatomite are fossilized remains of microalgae. So that's why maybe this is the reason why diatomite has this high amounts of vanadium. But because of the fact that it is so abundant in the sea, also seafood has comparably high amounts of vanadium. For example, mussels can have up to 5.14 milligram per kilogram dry weight in this case, but comparably high amounts, of course. To sum it up, I hope I could show you that most elements normally already have their origin in the raw material. So a lot of elements already occur in fruits, of course. Something where we haven't focused today on, but which is also important to know, is that growing conditions, soil, the use of fertilizers, because some fertilizers can contain amounts of cadmium, have also an effect on the concentrations later on in the raw material. Pineapples, for example, have very high concentrations of manganese, but also of some other elements, and this is most likely to do with the pH of the soil and the ion mobility, something maybe we could have a closer look at in the future. The dejuicing itself lead to a significant decrease of some elements, especially heavy metals are clearly decreased. Some nutritional elements, like for example potassium, is less decreased, and they are concentrated in the pomace, so that's why fruit juices contain significantly lower metals than the corresponding fruits. But in the case of some processing aids, some elements can be released into the product, especially filter aids are critical in this case, especially for example diatomite, which can release vanadium, but also arsenic, aluminum, iron, and molybdenum. And for example, like I said, bentonite can release a higher amount of lead into the product. Thank you for your attention. Any questions? Yes.
Do you try oranges? Orange juice?
No, we have some data on orange juice itself, but we haven't analyzed orange samples. But to be honest, I have to have a closer look at the data because I don't have it in mind yet. But orange juice, for example, is less processed, so it is a clean product. You don't have any processing aids which are used. It's a still cloudy product. As I remember right, orange juices are very low contaminated on heavy metals, but I haven't got in mind what the nutritional elements, minerals, how abundant they are in orange juice, for example, compared to pineapple, which has very high concentrations concerning all elements. But if you leave your data, your contact here, I can have a closer look at the data and I will tell you later on.
I'm curious about the techniques that you use for quantification.
Yes.
About the techniques that you use. There is one technique that is better than the other, or they are complementary, the ICP and the X-ray fluorescence?
Like I said, they are completely different techniques, but of course the results fit to each other, and sometimes, so for example, in case of the vanadium, we did this type of double check. We measured, for example, also the fruit juice by TRXF and by ICP-MS, because ICP-MS, all these techniques sounds quite easy, but they aren't, because there are always some interfering signals. For example, in case of ICP-MS, there are isobaric problems because of other elements which have different kinds of isotopes, which have the same molecular weight, or polyatomic interactions, for example, or double charged ions. So it's quite complicated, and so that's why we did sometimes, especially in case of these findings, this double check of these two methods.
And for example, if a company needs to decide one of the two equipments to make quality control, which recommend you?
Perlite. I recommend perlite. We saw by the use of this filter aid, I saw a little bit higher increase of the aluminum, because if I go back to, I haven't shown these data here, but perlite is rich of these aluminum oxides, and that's maybe why we find a little bit higher aluminum concentrations, but it is not a high increase to those concentrations which originally occur in these products, but the vanadium filtration has a very high impact. But to be honest, it is not really known. Maybe it is also good to have some products on the market which have a higher vanadium concentration, because of some animal studies, it is supposed to be essential for the body. And like I said, there are those data which say that we have an intake of 10 to 100 microgram vanadium per day. But I'm sure that this higher levels you can only increase if you consume beverages which are already high in vanadium, or what we also saw. But this is something completely different. If you have, like I said, soil has comparably high concentrations of vanadium, which in the same order of magnitude like zinc, for example. And if you have fruits which are not really washed, you have some soil particles still on the fruit. And if we analyze, for example, unwashed fruits, we find also quite high amounts of vanadium. But I don't know whether this vanadium, if you consume fruits which are not washed, like I said, if this vanadium is bioavailable, I don't know. So maybe it's important to have a technique which can be used to achieve a little amount of vanadium if it is essential.
Okay. Thank you.
Excuse me, have you seen any data of manganese in banana puree?
I have also data on banana puree, but we can take a look at later on. I don't have it in mind yet. Because it's normally at the same soil, so it should be also higher compared to, for example, other products, maybe.
Mm-hmm.
But this is also something I thought about, but I have to we can do it later on.
Okay.
Is there something known about the function of manganese in the plant?
Yeah.
Does it help the plant in some way, in this particular species?
It is important for the plant growth, as far as I know, but also in case of manganese at higher concentration, it could be also toxic for plants. Yeah. But it is important for plant growth.
For some enzymes as a cofactor.
But I don't know whether it is plant specific, so whether, for example, especially pineapple accumulates manganese more because it has some enzyme activity. I don't know.
Because as far as I remember, correct me if I'm wrong, the mobility of a plant, or also the access of the heavy metals into the plant and then the transport in the plant is quite heavily, is regulated very much, right? So you cannot push all the metals that you want into a plant. But for some, apparently there is an exception for manganese. And why manganese and not iron? You know, that's, I'm not sure if it's well understood. Interesting.
Yep.
Is it possible that these filter aids like diatomite and perlite absorbs nutrients or other compounds which are important, like potassium or magnesium?
In the kind, if you filter a juice, you would use also cloud particles. So it is less the effect that the filter aid absorbs these elements. Maybe this takes also place a little bit because if some elements are released, there are of course this negatively charged positions within the filter aid particle, and maybe other metals bind to this. But there's also another effect during filtration, because you would use also further cloud particles, so there is of course a reduction of other elements too. But those elements which have a very high mobility already, if you do this dejuicing step, for example in case of potassium, it is also not reduced much by the filtration step. But other elements, for example iron, which is already reduced quite clearly during the dejuicing, is also further reduced during the filtration step, because of the further reduction of ground particles, fibers, and so on.
And what about big molecules like mycotoxins? Maybe they are also reduced?
Yes, but that we already had a look at, because we have some cooperation with an institute in Germany, and then we have had a look at the interaction of mycotoxins and the different processing lines. We're going to publish this soon, and let me think. So there are different processing steps, and especially the use of activated charcoal and bentonite is able to reduce specific mycotoxins. The filtration step itself has a less impact. Of course, because of the filtration, also some amounts are reduced, so some amounts of the mycotoxins, but the step before this filtration, the treatment with the fining agent, has the higher impact, and especially activated charcoal in this case has a very high activity in absorbing mycotoxins.
Do you know which percentage is reduced?
But
From the original product, how much you can reduce the amount?
it depends on the kind of mycotoxins. We only had a look at patulin, ochratoxin A, and altenariol. Patulin was not good reduced by this step. It was only reduced by 20%. Other mycotoxins like altenariol and ochratoxin A, both were better reduced. So especially in the combination activated charcoal and bentonite and the filtration step later on, we reduced those mycotoxins to levels under the detection limit. Other processing lines with other fining agents, so I also showed this gelatine, silica sol, bentonite combination was a little bit less effective. There we reduced it to only 30% of the original concentration, but it was still very high impact. Yeah.
Okay, entonces, if there are no more questions, thank you very much, Bianca.